Good morning. Today's topic is separation between successive HQL planes. Subject is engineering physics, presented by lecturer rule number 37 from Data Science Department. Introduction to crystal planes. Crystalline materials are characterized by a periodic lattice structure where atoms are arranged in well-defined place, indexed by Miller indices (HKL). Each set of planes (HKL) represents a family of parallel planes with specific orientation and spacing. The separation between these planes is crucial in X-ray diffraction, electron microscopy, and material characterization. Miller indices are determined using reciprocals of intercepts of the plane with crystal axis normalized to smallest integers. Understanding this spacing is essential for predicting diffraction angles or interpreting structural data in material science. Miller indices and reciprocal space. Miller indices HKL are defined as reciprocals of intercepts of plane with the ABC axis of the crystal lattice. Reciprocal lattice vectors are directly related to Miller indices and are used to describe diffraction conditions in Fourier space. The reciprocal lattice vector GHKL has magnitude 2 pi by d, HKL and direction perpendicular to the HKL planes. The concept of reciprocal space simplifies the analysis of diffraction patterns in crystalline solids. In reciprocal space, each HKL plane corresponds to a point whose coordinates are multiples of the reciprocal lattice basis vectors. General formula for d-spacing. The interplanar spacing d HKL for any crystal system is derived from the matrix tensor and reciprocal lattice geometry. The general formula is 1 by d HKL whole square equal to h square by a square into 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. This full expression includes scale terms. This formula is derived using vector dot products between reciprocal lattice basis vectors. It reduces to simplified forms in higher symmetric crystal systems like cubic, tetragonal, and orthochromic. Accurate d-spacing calculation requires knowledge of lattice parameters a, b, c and interaxial angles alpha, beta, gamma. Cubic crystal system d-spacing. In cubic crystals, A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degree. The d-spacing formula simplifies 1 by d HKLL square equal to h square plus k square plus L square by a square. Thus, d HKL equal to A by under root h square plus k square plus L square, where A is the lattice parameter. It shows that the higher order HKL reflections have smaller d-spacing due to larger Miller index sums. For example, D100 A comma D100 equal to A by root 2, D111 equal to A by root 3, demonstrating decreasing spacing with increasing index. Cubic symmetry makes d-spacing analysis straightforward and widely applicable in semiconductor and metallurgical engineering. Tetragonal and orthochromic systems. In tetragonal systems, A equal to B, not equal to C, comma alpha equal to beta equal to gamma equal to 90 degrees, the formula becomes 1 by t h square h square plus k square by a square plus L square by c square. This reflects an anisotropy along the c-axis, causing different comprehensions stretching in this spacing. Orthochromic systems A not equal to B not equal to C, then alpha equal to beta equal to gamma equal to 90 degrees, use 1 by d hk L square equal to h square by a square plus k square by b square plus L square by c square. Each axis contributes independently, so d spacing depends on relative magnitudes of a, b, c and d. C. These systems are common in perovskites in layers materials and d-spacing affects electronic and optical properties. Each axis contributes independently, so d spacing depends on relative magnitudes of A comma B comma and C. Of A comma B comma and C. Hexagonal and rhombohedral systems. In hexagonal crystals, A equal to B not equal to C comma, alpha equal to beta equal to 9 degree, then gamma equal to 1 2 degree, use 1 by t h k scale 4 by 3 into h square plus hk plus k square by a square plus l square by c square. Then 4 by the factor arises from the 120-degree angle between an A and B axis modifying the in-plane component. Rhombohedral systems A equal to B equal to C, then alpha equal to beta equal to gamma not equal to 90 degree. Use a more complex formula involve cos alpha. In hexagonal systems, 100, 100 and 001 planes have vastly different displacement affecting anisotropic behavior. Monoclinic and triclinic complexity. Monoclinic complex systems A not equal to B, B not equal to C, comma, then alpha equal to gamma equal to 90 degrees, then beta equal to beta not equal to 90 degrees. Introduce of diagonal terms in the metric tensor. The displacing formula includes cross terms like HK and HL due to the non-orthogonal beta angle. Triclinic systems, all parameters difference. For metric sensor, the HKL calculation, the systems are common in complex oxides, biomaterials, but pose challenges for diffraction analysis. X-ray diffraction and Bragg's law. Bragg's law n lambda equal to 2d HKL sin theta, with lambda is an X-ray wavelength and theta is the glazing angle. This equation shows that d HKL determines the diffraction angle theta for a given lambda and order n. Measuring theta allows experimental determination of the HKL, enabling crystal structure identification. Peak positions in XRD patterns directly correspond to HKL planes, and the despacings precisions in despacing measurement enables strain and defect analysis engineered materials. Applications in thin films and epitaxy. Electron microscopy and despacing design primitive cubic cell, face centered cubic lattice, body centered cubic lattice, primitive cube lattice, primitive cubic lattice, face centered cubic lattice, body centered cubic lattice. Miller indices for 3 types of cubic lattices. 3 types this is. Please observe figure clearly. This is 100 planes, 110 planes, 1111 planes. 200 planes, 220 planes, 111 planes. 200, 110, 222 planes. There's 3 planes. Neutron, this is the figure. You can observe in figure clearly when the angle of x-axis, y-axis, z-axis, alpha is 90 degrees, beta is 90 degrees, gamma is 120 degrees. In this case, it touches its origin. Despacing, entropy, and material properties. Despacing entropy affects thermal expansion. Anisotropy affects thermal expansion, elastic moduli, piezoelectric coefficients. For example, in graphite, D002 less than D100 and less this leads to highly anisotropic thermal conductivity. Defects and D-spacing perturbations, point defects, vacancies, XRD lines boarding. Quantifying these effects is essential for failure analysis and microelectronics. Silicon and microelectronics. Silicon has a cubic diamond structure with A equal to 5.431, a semicolon D111 equal to 3.135, A D220 equal to 1.90, A. XRD and TEM confirm D-spacing uniformity critical for device fabrication. Non-implementation introduces strain detectable via D-spacing shifts in XRD strained layers. But emerging trends and challenges. 2D materials, graphene have tunable interlayer despacing via Van der Waals engineering. Topological insulators exhibit surface states sensitive to despacing and strain. Challenges including measures of a despacing changes and resolving overlapping HKL peaks. Okay, thank you.